Thank you very much. I'd like to thank Dan Sherson for the session together. Dan is also on our Science Advisory Board, so gives us lots of advice. What I'm going to do is really give an overview. So some of you who are here this morning will see some of the same slides again, because in their wisdom, somebody put two of my folks' talks before my talk. But this is what they say, tell it once, tell it again, and maybe you'll remember it then. Our leadership team, where does this thing work? Oh.
Or is it that button up different?
There we go. Okay, so our leadership is Glenn Amatucci, Karina Chapman, who you heard from this morning, Shirley Meng, and Yetming Chang. Okay, and these all are units within the EFRC. There's one missing on here. UC Berkeley is also within our system now that Gert Cedar moved. You saw this one this morning. This is the overall mission of the center. We are basically trying to understand all electrode reactions, good ones, bad ones, indifferent ones. And if we can do that, then we should be able to improve the electrochemical performance, come up with new materials. And we're going to do this from atomic level all the way through the operating battery and from nanoseconds to years. And we've kind of spread this across on this one. This is the length scale working on atoms up to the full battery, and on the time domain from nanoseconds, again up to years. And our EFRC is focused purely on cathode materials and purely on intercalation materials. So materials of this sort, typically the layered oxides, layered sulfides, and so on. You all know that battery reactions are complex. Battery electrodes are living things. It's not just the lithium that moves, everything else moves as well. So what we do is choose some model compounds, and we choose these very carefully to be typical of the systems we're looking at, and yet simple enough in principle that we can fully understand what's going on. So why are we doing what we're doing? If you look at today's batteries, they're extremely limited in their energy storage. In fact, if you look at them, none of them exceed 25% of their theoretical capacity, and that's based on a weight basis. So the most well-known, the longest-lived one is up to 25%. If you look at the volumetric capacity, it's down to 19%, and many of the other systems are 11, 15%. We're asking ourselves, why is this the case? What's stopping us achieving a much higher values? And there are a number of issues. I don't really want to go into the anode, but carbon's obviously a big issue. We need a much higher lithium content in the cathode. In other words, you've got to cycle at least one lithium per redox center, and ideally up to two, and I'll talk about both these. And we need much better transport behavior. If we had higher ionic conductivity, higher electronic conductivity, then we could use thicker electrodes and reduce the number of current collectors, separators, and so on. So we're really interested in the transport properties. If you're interested how these numbers came about, whoops, let me go back a second. They're all in this review article, which is the centennial journal publication of IEEE. All those articles are free on the web, and they go back 25 years and go forward another 25 years. So here is what our goals are. We're going to understand all the reactions. Okay? We're going to, as Shirley mentioned, we're going to close the gap between theoretical and practical energy density. In this case, we're using NCA and NMC as the model compound. We've chosen those two predominantly because we can get large quantities of reliable, reproducible materials, and we don't have to make it all ourselves. As we go further down the pike, we'll start making specific compositions or specific morphologies as we need them. Our second goal is to get reversible multi-electron transfer, and the model compound I'm going to be talking about shortly is vanadium phosphates. And this complements what we're doing in JECS, and we have a number of folks in our EFRC who are also in JECS. JECS is doing exactly the same thing, but they're looking at 1 magnesium. We're looking at 2 lithium. We think ours is a more pragmatic approach. We've got a lithium anode, we've got a lithium electrolyte, we just have to worry about the cathode. Okay? And I'll show you, I think we're on the right track. I've already mentioned we're going to look at limiting transport in the positive electrode, both ionic and electronic. And the initial goals was to enable new chemistries. As all the directors in the room know, we initially had 5 years, they cut us back to 4 years. So it's unlikely we're going to get to that within the 4 years. And that, let me emphasize again, we're talking about intercalation reactions and we're talking about cathodes. So this is how we're structured. Okay? So in the end, what we're saying is what is the ultimate limit of intercalation reactions? What is stopping us from achieving those ultimate limits? And we're doing this by having a fundamental study of the reactions, the structures, and the phases of model compounds. And I'll come back to more of that in a minute. And what we use are interdisciplinary teams. We have theorists, experimentalists, and characterizers. And I use that in a very positive manner. Okay. So we're divided into 3 thrusts. Thrust 1 is focused on the material itself. Okay. And we've got 2 model compounds here. In this focused interdisciplinary team, 1.1, which Shirley leads, this is the closing the gap on the layered oxides. On 1.2, this is the 2 lithium intercalation, which I lead. And thrust 2 then looks at the whole system. So we're looking at from the point of view of the electrode. And I won't say too much more about this today, but Lewis Piper has a talk tomorrow and a couple of talks on posters later in the week, and I'll mention all those in a minute. And then we have a cross-cutting thrust, which is this characterization, and we put a lot of emphasis on operando techniques. So this is not meant to confuse you. This is meant for the fast writers so they can take down all the other papers related to our EFRC that are being presented this week. So I said in the thrust 1, I lead it. This is material-centric. Fit 1 is the layered oxides. Shirley gave her talk just before lunch. Okay. The beyond olivines, which is 2-electron, which I lead. I'll give you an overview now. We had one presentation this morning on stability, another one this morning on hydrothermal synthesis. Boa Wen is giving a talk on Thursday on doping of the vanadium phosphates, and Nick Quackenbush has got a talk also on Thursday on interfacial effects in these materials. So we've got a lot of talks on these materials. On thrust 2, where we're establishing the local meso-macro scale continuum. This is a system-centric one. Lewis Piper has a talk tomorrow, and Zalis has a talk on Thursday, or is that a poster? Poster, okay. So that's an easy one. You can find that one in your spare time, okay? And the FIT 2.2, Yet Ming Chang is leading that effort. Then on the cross-cutting characterization, you heard from Karina Chapman this morning, describing what we're doing there. Then throughout all these, we have theory. After our experience in round 1 of the EFRC's NECCES 1, where we had a separate theory thrust for 2 years, it wasn't really effective that way, so we integrate now the theorists directly into each of these FITs, so there's a theorist in each one of these activities. Okay? And you're going to hear from Xiping Ong tomorrow. You heard this talk yesterday. You may have heard this talk yesterday, and then we got a thermodynamics talk on Thursday. So there's a lot of talks that you can look up the abstracts or go to still. So let's look at the layered oxides very briefly. There's several issues here. Why are these limited in capacity? Okay. As Shirley said this morning, the maximum capacity, and I'm going to say in operating cells, not in what labs claim and all the rest of it, in real operating cells, is somewhere about 170, maybe 180 if you're lucky. Okay. This is about 0.6 to 0.7 lithium. The NMC is used in the BMW cars, and NCA is used in Tesla cars. So it's out there being used, but there's about at least a third to 40% of the capacity not being used. Okay. If you look at all these different compositions of NMC, you'll see the open circuit voltage, the free energy reaction are not too different, and about at this point they start crossing over. And what we're really interested in is going further and further up here, and we know from our past results, the higher you push the charging voltage, the faster the fade rate. So we're going to try to understand exactly what is going on there. So let's just look at what we propose to do and what basically Shirley is going to be doing on. Why can't we get more out? What's the real reason? And this is the structure, and it's not really like this. Okay. This is what it ideally is. The transition metal is here, the oxygen's all here, the lithium's in here, and nothing moves. Well, entropy dictates otherwise. So some nickel always comes down into this layer, and it turns out if you're actually making batteries, you want a certain amount of nickel in that layer. If you can get 2%, 3% of the nickel into this layer, then it stops these sheets from moving relative to one another. This is what Anton's group talked about yesterday. You don't want these sheets shearing. So basically you just like some pillars like you have in buildings to stop this happening. So what we're looking at is different phase equilibria, how they evolve on cycling, on resting, what are the thermodynamics versus the kinetics of these reactions, what are the stability of the different phases. Is the 3-block phase or 1-block phase more stable than the other one? At what point should they switch over? And how do you prevent them from doing so? We know the transition metals move. Now, 10 years ago, people said they don't move, but we all know now that transition metals move as you charge and as you discharge, moving all the time. The other issue in here, as Shirley mentioned, is the oxygen activity. If you take all the lithium out of cobalt oxide or nickel oxide, the partial pressure of oxygen in those materials is probably well over 1 atmosphere. So you just need a catalyst to get that going, and you've got a real problem on your hands. But no one's actually measured those things. The other issue is how much of the redox in these materials at high voltage is actually on the oxygen and not on the transition metals. We have to pin that down once and for all. If you read the publications, they're all over the place. Okay. And then we have the whole issue of defects, whether these are point defects, extended defects, what happens when you put lithium in and out, strain-stress relationships, what does that do to the material? And the way we're going to approach this is how we did it. In the previous 5 years, we had modeled compounds of lithium iron phosphate and iron fluoride, and intercalation and the conversion reaction. We're going to put a lot of stress on operando characterization. We found out that what you see after a cell equilibrates is not the same as what is in an operating cell. We're going to use model compounds. I've already mentioned NMC, NCA. We integrate theory totally within that, so the theory is helping to tell us as experimenters where we should go, and they can confirm afterwards if we come up with some ideas, experimentally, do they make sense or not. We're also looking a little bit at this high voltage spinel, because this high voltage spinel seems to be much more stable than either one of these two at high voltages. Why? We've got to find out what's going on there. And if we can find out what's going on, then maybe you can translate it to these other two. Shirley's already shown you this. This is just a pictorial vision of the same sort of things. We're looking at it at the atomic level. We're looking at the oxygen chemical potential. We're looking at the phases. And then we're looking at all sorts of defects using all these different techniques down here. We don't develop techniques in a vacuum. We have an issue that we need to study, such as dislocations. We look at what technique could address that. And then our technique experts push the frontiers of that area forward so we can actually see what's going on. Shirley also showed this slide. This is typically the number of people we have working on any one of these FITs. It's not to say that they're all just on this team. Several of these people are also on the other one. So people are on multiple teams, but they work together. And these people video conference at least once or more a month as a team. So they interact together, exchange data, exchange ideas, and the normal things you do when you disagree with other people about the interpretation of the results. So we have meetings here to do that as well. But this is a fairly typical grouping. As Shirley mentioned, we have a couple of folks here. I don't know whether we call them on loan. They're associate members. So if we've got an expert next to us, we're going to use them. Now, they get no resources. We may lend them one of our postdocs to work with them. So we have basically a postdoc working between Guangwen Zhou and Eric Stack at Brookhaven on the in situ studies in the TEM there. Let's switch to the next major goal of ours, and that's this multi-electron transfer. Can it be done? It wasn't clear a few years ago. If you look back in the literature, probably before many of you were born, the layered sulfides, in particular vanadium diselenide, cycle 2 lithiums forever. Mike Thackeray looked at some titanium-doped layered oxides and showed you could get 2 lithiums in and out of them. But there's very few compounds where this has been shown, with one exception. Vanadium pentoxide has been around since 1970, 1968. It had all the mechanisms wrong, but it reacts with 2 or 3 lithium. So vanadium is a little bit unique. So already mentioned, we're looking at 2 lithium. This complements what JECS is doing. And we tried to get some clues as to what we should be doing, what materials, and this is some work that Gerd Ceder's group did maybe 3 or 4 years ago. They did calculations of all the couples for phosphate materials, and you'll find they got another paper on sulfates and things like that. But they did this one, and what you really need theoretically in the cell is somewhere over 800 watt-hours per kilogram to get a decent cell package. DWE and others say maybe 600 will do it. Also, you can't go above the red line. This is about 4.5 volts. That's the stability limit of most electrolytes. So if you look at phosphates, there's not too many choices. So here is lithium iron phosphate right on this bottom line. Lithium manganese phosphate gets in here, but we know that doesn't work too well. There's a hypothetical copper phosphate, which I think people have tried to make and haven't succeeded, which might be interesting. So what we started looking at is couples of these. So we've got iron 2 plus 3 plus here, iron 3 plus 4 plus up here. So we said if we combine these together, 2 lithiums, 2 electrons, we can push ourselves over here. So we in fact looked at the iron as a power phosphate. This one cycles fine. This one is over 5 volts, and we can charge it forever, and all we're doing is reacting with the electrolyte. We can't get that second lithium in and out. BOA, when in my group looked at molybdenum compounds, and again, the power phosphate, we can only get about 1 lithium, or less than 1 lithium per molybdenum, so that one didn't work either. So we put our emphasis on these two, vanadium 3, 4 plus, vanadium 4, 5 plus. If you add these two together, you get over here. So this is why we looked at this one. There was a talk earlier this week on a vanadium oxide with a fluoride and lithium in it. These systems are fairly well known, have been known again, I would say about 1980 when we understood the mechanisms. All the vanadium oxides, you deep discharge them, switch over to rock salt. So the lithium and the vanadium is totally randomized in the structure. The problem with that is the voltage profile goes from about 3.5 volts down to 1.5 volts. It looks almost like a supercap. So some people would say It's not good storage. So why did we choose this VOPO4 as our model compound? We published back in 2005 some initial electrochemistry, and we start with this hydrogen vanadial phosphate. You'll see this written in literature as VPO4 H2O. I don't think there's any evidence of H2O in there. It's hydrogen in there. This was first made by Alan Jacobson. He heated this material and made this epsilon VOPO4. And back in 2005, we said if this material is really good, we should better get this hydrogen out electrochemically. So we built an electrochemical cell with this material, charged it up somewhere over 4 volts, and all the protons come out. And then when you discharge it, you then put lithium in. So we could cycle this at about 4 volts in and out. We then said, okay, we had 2 hydrogens in there. Why can't we put 2 lithiums in there? So at that time, here is the first cycle, about 4 volts, and the second redox couple is about 2.5 volts. And you see in the first discharge about 250, and it's down to about 200 in the second one. So that was some indication that there was something interesting here. Valence was looking at a fluoride analog of this at that time. We were discouraged from working on this further by our sponsors. We don't like vanadium. So we stopped for about 5 years until they said, why aren't you working on vanadium? So we went back to it. So the approach we're taking here is, I said, doing everything. So we have synthesis, we do electrochemistry, we look at the structural evolution. This is mostly done with argon using PDF and other techniques. We look at the kinetics, ion electron transport, and my colleague from San Diego will talk about this tomorrow and touch on some of these others. And what we do is integrate the theory, the measurement, and the synthesis all together. So if you heard the talk this morning, I'll get to a minute on the stability of these materials. We found some things in the stability issues, then theory said, this makes sense. So as I say, we've got an integrated team of experimenters, theorists, and characterizers in this one. We looked at the stability of all these phases. This is stable at room temperature, this epsilon phase. And for those of you who are not familiar with these materials, there's total confusion in the literature because whether you see alpha, beta, gamma, delta, epsilon here depends which one was discovered first. Okay? So alpha VOPO4 does not give you alpha LiVOPO4. Okay? So we're busy trying to change it, so we're saying we're going to take the parent structure, VOPO4. If that's epsilon, then the lithium analog is epsilon as well. In the literature, you'll find this called alpha. The calculations on the 2 lithium ones showed this was polythermodynamically unstable, but kinetically stable. So there may be some issues there. I'll show you some data showing these materials are much more stable than NCA and manganese phosphate. We've made these materials by a low-temperature hydrothermal technique as well as by a high-temperature method. Okay. So we've made both the epsilon unlithiated and lithiated form and characterized them. We've got good electrochemical data. By good, I mean we can reproduce it and the capacity is right. It's by no means perfect. And there are in situ studies underway right now. And right now, the experiment and theory on calculated voltages, structures, all agree with each other. So once we fully understand this one, then the challenge comes, what's next? What's the next system? So just to give you some impression, VOPO4 itself, there are at least 6 different phases. On this H2 VPO4, which we start out with, there's 2 versions of that. There's a monoclinic and the tetragonal version. And you can see there's some CV here. The black one is the epsilon VOPO4 from the monoclinic, and the red one's from the tetragonal. And you can see one is much more well-defined than the other one. Okay. And here's the SEM pictures of these two. The monoclinic form, which is all small separated particles. The trigonal form forms these large spheres, just like you see in NMC. Okay. This is now is just cyclic voltammograms at different rates, and this shows that there's a diffusive mechanism, and we've calculated diffusion coefficients from this, and they're quite reasonable. So this just shows you the first cycle of material formed by these two different techniques. So we started here, this case, we started with one lithium in the structure. These were charged, so we took the one lithium out, and the red one's the hydrothermal, and you can see we're getting about 150. This is almost exactly the calculated value, and when we put it back in, we get another 150 down here. The theoretical value is about 320. We're getting 308, so it's very close to theoretical with this material. The high temperature material is in the blue, and you can see the capacity is slightly less. But the key thing to notice here is we have three different steps here. So we have a phase at lithium 1, a phase at lithium 1.5, a phase at lithium 1.75, and a phase at lithium 2. So there's lots of different phases in this material. And we're not the only ones that found this. The French group have found this, and Mantram in Texas has seen the same thing. So we now actually look at how this material cycles. And initially we did this just over each voltage plateau itself, so not to stress the material. So this is over the 4-volt voltage plateau, and this is some older data, and we're getting about 100 milliamp hours per gram here. Nowadays we're up to about 130. This is over the lower voltage plateau. We can see all these steps, and we're getting essentially theoretical. On the discharge, there's something strange going on here, and we haven't seen this again on these materials, and I'll show you there is some issues there. But over 25 cycles, this material is very comfortable cycling over the two separate regions. So what happens when we do it over both steps? You see now, this is at CO of 50. We're getting about, in this case, about 240 milliamp hours per gram, and at CO of 20, it's in fact slightly higher. Okay. And I suspect if we push the rate a bit up, it may go still higher. And this came up in the earlier talks on vanadium oxides. There are some side reactions going on. The lower the length of time you have these materials at the highest voltage, the better off you are. So we have to solve those issues. But the principle here is we've shown that these materials are capable of cycling many cycles without totally falling apart. What about their stability in cells? We all know NCA is a problem, even though it's commercial. So what we did, and this was in Eaton's talk this morning, if you went to the safety talk, and not many of you were there because it was held in a closet that held maybe 20 people total. So what we did was looked at a series of cathode materials by themselves, and then with the electrolyte, and in some cases with the solvent alone or with the electrolyte salt. And then the critical thing is, contrary to what you'll read in the literature by some very well-known people, you've got to limit the amount of electrolyte or everything is dominated by the electrolyte. If you want to see what the cathode is doing, you've got to limit it. So if we have a LiVOPO, VOPO4 without any electrolyte, there's no heat released. This is this black line here. We put lithium-2 without electrolyte. Again, there's no heat release. These materials are totally stable by themselves. Okay? If we put electrolyte with them, you see now the lithium one here, we're getting some heat released. This is about 156. The one with 2 in is releasing somewhat more. Okay? I should say a fair amount of this is coming from the electrolyte, not just from our material. So these materials are stable, and just to show you how stable we're talking about is, this is compared with NCA. Note the difference in axes here. So the worst one here is 1 watt per gram. Over here with NCA, we're talking 5 watts. So if you get NCA all by itself, no electrolyte, this is charged material, you'll see it evolves oxygen and evolves heat at about 230 degrees centigrade. If you put electrolyte in with it, it evolves even more. So there's some reaction going on here. And you can see the amount of energy released, around about 700 compared with about 100 here. So very, very different scales. So we looked at a series of these. NCA is the least stable. Manganese iron phosphate comes next, then iron phosphate. And these two are essentially totally stable. Okay. But you'll notice there's this little thing up here. If we look at VOPO4 itself, the situation isn't quite the same. So if we get VOPO4 with no electrolyte, there's absolutely no heat release. That's our black line here. Okay. If we put VOPO4 just with the solvent, we get this blue line, so we're getting some reaction about, was it 270 and over 300, and it still hasn't finished at this point, and we're getting 135 joules released. If we now add to that the LiPF6, you can now see releasing 407, so much more. So something's going on here. Eden's done a fairly intensive structural study. What we find out, if you get VOPO4 in the electrolyte, it reacts to giving you HVOPO4. If you keep this going, you'll then get another hydrogen inserted in here. So this material is safe in the sense it's not releasing oxygen, it's not going to burn anything up, but it is in fact taking hydrogen out of the solvent. And what we think is happening here is that the LiPF6 is accelerating this reaction. So this is something we're going to have to be aware of. If these cells get hot, we have some issues. Calculations have been done by a colleague at UCSD, and they agree totally with what we see here. You would predict this should happen. This should be no surprise. Vanadium phosphate is an oxidation catalyst used in the chemicals business. Okay. Let me very quickly, in the last couple of minutes, just go through the characterization. I said this is our cross-cutting thrust 3. Karina talked most about it, so I'm just going to run very quickly through it. So in our first 5 years, we developed I would say, a unique set of in situ and ex situ techniques, well beyond the state of the art. We had in situ NMR, Claire Gray was doing. We had in situ TEM, looking at reactions of conversion materials, and we had a whole series of synchrotron stuff, and we really did the first in situ PDF studies of battery electrodes during that period. In this next 4 years, we're going to keep this going, looking at a range of different things. In particular, we're going to move from solid-state cells to liquid in situ cells, and this is going to be basically going on mostly at Brookhaven. And we've talked on these now, only a couple of minutes left. You've seen this picture from Karina. We're looking at the atomic level, the particle level, and the whole cell level. Karina again touched on this. This is the so-called Ampix cell, which we designed, which is now used by a number of different people at Argonne. You can use it for different techniques. We can put samples in here, and we're pretty sure we're measuring what is actually happening in the cell and not some other spurious thing because it's delayed for one reason or another. And these are all highlights of our EFRC. I think these are all available on the DOE website if you want to look at them. Karina also talked about this little issue here. If you look at cells the wrong way, just like if you look at your kitten the wrong way, you'll get a response. So here, if you put X-ray beams on your sample, it's going to do things. We know for sure when we put our TEM on samples, we can see things happening under the TEM beam. So one has to be very careful you're getting meaningful results out. So just to conclude, in our first go-around, we used these as the model compounds, and I think these showed the direction to go is to use model compounds, is to use operando studies, and for intercalation, our bottom line was you want a single-phase reaction, whether it's metastable or stable, doesn't really matter. Okay. I think we're showing that 2 electron redox couples are possible, and that probably we can get to about 350 watt-hours in full cells. And the big challenge is closing this gap in the layered oxides. We think it can be done. Whether we can go all the way is a different issue. If we can do that, then we can get to 1 kilowatt-hour per liter. That's not quite double today, but that's going to be the ultimate limit, we think. The other thing, our conclusion is, you've got to use operando tools if you're going to be looking at battery reactions. And you've got to use theory in guiding the experimental direction you're taking and in confirming your experimental results. And some of this data I've shown is in this chemical review. Last December, this special issue is all on batteries and nothing else. So if you need a primer in batteries, get hold of this issue. And I'll stop there. Thank you very much. And this is where you can contact us. And this morning you showed a picture of our group. We were sat here. This is where our labs are, and this is where our offices are in a brand new building. And in theory, it has solar cells on, but they ran out of money before those got on.
Is that an actual picture, or is that a computer?
That was an artist's rendition.
Okay.
So we don't have the green grass either, because they found that on other buildings. It's a nightmare. Don't put grass on your roof.
Okay, well, is talk is open for discussion?
And what your results with the lithium vanadium phosphate is showing is that when you go for multi-electron transfer, multi-lithium transfer, you have this large change in voltage.
Yes.
For example, you're going from 4 to. So, I don't know, from a practical point of view, such materials may not be that attractive. And the other thing is that in many cases, because of these phase changes, your reversibility is not that good. So, I don't know, what is your long-term view about multi-lithium based interpolation electrodes for
Well, say at the moment, these materials are cycling perfectly over the 2 lithiums. Whether we can get 1,000 cycles out, only time will tell. But it's not the purpose of the EFRC to do 1,000 cycles. We're trying to understand what's going on. We raised this issue about 10 years ago when we first published this about the 2 steps, and all the electrical engineers said, stop worrying about it. You've got multiple cells, you've got DC to DC converters. We handle all of that all the time.
I know, the efficiency will be very low, anyway.
Those folks weren't worried at all about that. They're far more worried about how much energy can you stack in a given volume.
For example, when you go in spinel manganese oxide, you go from the 4 volt to the 3 volt, you have 2 phase and they're on cycle.
Right. Yes.
That is characteristics of multi-electron.
Yes. These materials are 3-dimensional structures. The structures do not change much as you go from one phase to another. There's some slight twisting of the tetrahedron and octahedron, but the structures themselves don't really change. And that's a big plus.
Are there any other questions? I would just say, I don't know if it was my own confusion, but I thought when you're looking at the couples for vanadium for 3, 4, and 4, 5, did you have the 3, 4 couple at 3.7 volts? Because when you're cycling, you were seeing that other plateau at 2.5 volts. Did I miss something, or is that?
No. We measure voltages. Go see to calculate them.
Okay.
And he says they're not quite right in some of these cases, so they have to assume an average structure. So when he calculated these weren't based on an actual structure.
Okay.
And our colleague who sat back in the room somewhere there from San Diego has done all the calculations, and they're now spot on. Now he's got the right structure.
Okay, very good. Okay, well, thank you very much. So